Welcome to G Fun Facts Online. Today, we are going to change the way you visualize the universe. Imagine the cosmos as a vast, dark ocean. For centuries, humanity has peered into this ocean through a narrow straw. We pointed our telescopes at specific stars, nebulae, or galaxies, marveling at the incredible details in those tiny pinpricks of light. But in doing so, we missed the grand tapestry. We missed the context. The optical light that our eyes evolved to see is easily blocked by cosmic dust, hiding the nurseries where stars are born and the cores of galaxies where monsters lurk. To truly understand the universe, to map its structure, trace its history, and uncover its hidden constituents, we needed to change two fundamental things about how we observe. First, the type of light we collect, and second, the width of our gaze. This is the story of wide-field infrared astronomy. This discipline is the killer app of modern astrophysics. It is a technological and scientific revolution that has transformed our view of the cosmos from a series of isolated snapshots into a panoramic, high-definition movie. It trades the narrow, piercing gaze of observatories like Hubble or the James Webb Space Telescope for the sweeping, all-encompassing vision of survey telescopes. This is how we found the coolest stars, the most distant quasars, and the dark energy tearing the universe apart. To understand why this is so important, we have to start with the physics of light. Visible light, the kind you see with your eyes, spans from 400 to 700 nanometers. This is the light of hot stars and energized gas. However, the universe is a dusty, expanding, and often very cool place. Infrared light, which spans from 0.7 microns to hundreds of microns, offers three critical superpowers that visible light simply cannot match. The first superpower is transparency. Cosmic dust is composed of silicates and carbon, effectively rock and soot. To visible light, this dust is opaque. It acts like a thick smog, completely hiding the center of our Milky Way and the dense cocoons where new stars are forming. However, infrared wavelengths are physically larger than these dust grains. This allows the light to wave around the grain and pass through relatively unimpeded. When we switch to infrared, the dark lanes of the Milky Way vanish, suddenly revealing billions of stars and the chaotic frenzy of the galactic center that were previously invisible. The second superpower is the ability to see the cool universe. Objects that are too cool to shine in the visible spectrum glow brightly in the infrared. This includes brown dwarfs, which are failed stars that never ignited, protoplanetary disks, which are solar systems in the making, and asteroids in our own solar system. The peak thermal emission of an object at room temperature is roughly 10 microns, which is deep in the infrared. If you want to see things that aren't burning hot, you need infrared. The third superpower is regarding cosmological redshift. As the universe expands, it stretches the space between galaxies, which also stretches the light traveling through that space. The ultraviolet and visible light emitted by the very first galaxies formed just after the Big Bang has been stretched or redshifted into the infrared by the time it reaches us billions of years later. To see the dawn of time, we are physically required to look in the infrared. Now, let's talk about the second part of the equation, the wide field. Most famous telescopes are pointing observatories. The James Webb Space Telescope, for instance, has a relatively small field of view. It is a sniper rifle, designed to study a specific target with extreme precision. Wide-field telescopes are the shotguns or floodlights. They sacrifice some resolution or depth to capture massive areas of the sky in a single exposure. This is crucial for three reasons. First, it allows us to find rare objects. If only 1 in a billion stars is a rare quasar, you cannot find it by pointing at random spots. You must image the entire sky to find that needle in the haystack. Second, it allows us to map large structures. Mapping the filamentary web of dark matter or the spiral arms of the Milky Way requires a scale that covers thousands of square degrees. And third, it opens up the time domain. By scanning the sky repeatedly, wide-field instruments can detect transient events, like exploding supernovae or moving asteroids. The history of this field is defined by a progression from rudimentary single-pixel detectors to the gigapixel cameras we have today. The Pathfinder was the Infrared Astronomical Satellite, or IRAS, launched in 1983 by NASA, the Netherlands, and the UK. It performed the first-ever all-sky survey in the infrared at 12, 25, 60, and 100 microns. Before IRAS, we knew of only a few infrared sources. IRAS cataloged over 350,000. It discovered the infrared cirrus, which are wisps of warm dust floating in interstellar space, and identified the first debris disks around stars like Vega, hinting at the existence of exoplanetary systems long before we found the planets themselves. While space is the ideal place for infrared because there is no atmosphere to block the heat, the ground has played a massive role as well. Between 1997 and 2001, the 2-micron all-sky survey, or 2MASS, used two 1.3-meter telescopes, one in Arizona and one in Chile, to map the entire sky in the near-infrared. 2MASS was revolutionary, not just for its hardware, but for its data. It produced a catalog of 470 million point sources and 1.6 million extended sources like galaxies. For 2 decades, if an astronomer wanted to know what an object looked like in the infrared, they checked 2MASS. It unveiled the true structure of the Milky Way, showing us definitively that it is a barred spiral galaxy, and it defined the L and T spectral classes of brown dwarfs. Then came the Great Hunter. In 2009, NASA launched the Wide Field Infrared Survey Explorer, or WISE. It was the spiritual successor to IRAS, but with vastly superior technology. Orbiting Earth, it snapped a picture every 11 seconds, covering the whole sky in 4 wavelengths. WISE was a discovery machine. Its sensitivity allowed it to find the white dwarfs, stars so cool they are essentially room temperature. It discovered the first Earth-Trojan asteroid. Even after its hydrogen coolant ran out, it was repurposed as NEOWISE, becoming humanity's primary sentinel for tracking near-Earth objects that could pose a collision threat. WISE cataloged over 750 million objects, creating a legacy dataset that astronomers mine to this day. So how do we build these machines? Wide-field infrared astronomy relies on 3 pillars of extreme engineering: detectors, cryogenics, and optics. The heart of modern infrared instruments is the mercury-cadmium telluride detector. Unlike the silicon CCDs in your phone camera, which stop working beyond 1 micron, mercury-cadmium telluride sensors can be tuned to detect infrared photons with incredible efficiency. The state-of-the-art sensors, such as Teledyne's H2RG and H4RG, are 4-megapixel and 16-megapixel arrays that have low noise and high durability. These are the retinas of modern missions. They allow for non-destructive reads, meaning the onboard computer can check the pixel's charge multiple times during a single exposure to remove cosmic ray hits and reduce noise. The second pillar is cryogenics. Infrared radiation is essentially heat. If a telescope is warm, it glows in the infrared, blinding its own detectors. This is why infrared telescopes must be cooled to cryogenic temperatures. This is done via passive cooling using huge sun shields like on JWST to perpetually shade the telescope, allowing it to radiate heat into deep space and reach temperatures around 40 to 80 Kelvin. For mid to far infrared observations, we need active cooling, using cryocoolers, which are mechanical refrigerators, or consumable coolants like liquid helium or solid hydrogen to drive temperatures down to near absolute zero. The third pillar is optical design. Building a telescope that provides sharp images over a wide field is optically difficult. Traditional mirrors suffer from aberrations like coma and astigmatism at the edges of the image. Modern wide-field telescopes use complex 3-mirror anastigmat designs. By bouncing light off 3 curved mirrors, engineers can cancel out optical errors, creating a flat, sharp focal plane over a huge area. This is the secret sauce that allows future telescopes to have the same sharpness as Hubble but a field of view 100 times larger. The current king of this domain is Euclid. Launched in July 2023 by the European Space Agency, Euclid's goal is to map the dark universe. It is surveying 15,000 square degrees, which is over a third of the sky, to measure the shapes of 1.5 billion galaxies and the precise distances of 35 million galaxies. Its NISP instrument, the Near-Infrared Spectrometer and Photometer, holds one of the largest focal planes of infrared detectors ever flown. It uses 16 H2RG detectors. In photometry mode, it images the sky in 3 infrared bands. These colors, combined with visible data, allow astronomers to estimate the distance to billions of galaxies via photometric redshift. In spectroscopy mode, NISP puts a grism, which is a grating prism, in the light path. This smears the light of every star and galaxy into a small spectrum, allowing it to measure specific emission lines like hydrogen alpha to provide precise 3D coordinates. Euclid released its first images in late 2023, and they were stunning. The Perseus cluster image demonstrated Euclid's ability to capture huge swaths of the sky while resolving tiny, faint background galaxies. It proved that wide field does not mean low resolution. But looking ahead, the next 5 years will see the launch of 2 NASA missions that will fundamentally alter our understanding of the infrared universe: SPHEREx and Roman. SPHEREx, launching around 2025, is a unique mission. Unlike Euclid, which is primarily an imager, SPHEREx is an all-sky spectral surveyor. It will map the entire sky in 102 different infrared colors. Effectively, it gives every single pixel on the sky a spectrum. Its science goals are profound. First, it will test inflation by mapping the 3D distribution of galaxies to look for non-Gaussianity, a subtle fingerprint left by the physics of the Big Bang's first fraction of a second. Second, it will measure cosmic ices, analyzing the absorption features of water, carbon dioxide, and methane ices in the clouds forming new stars, connecting the chemistry of the galaxy to the origins of life. And third, it will measure the extragalactic background light to determine the total light output of all galaxies over cosmic time. Then there is the Nancy Grace Roman Space Telescope, launching around 2027. If Hubble is the crown jewel of NASA, Roman is the empire. Named after the mother of Hubble, this telescope uses a 2.4-meter mirror, the same size as Hubble's, but with a field of view 100 times larger. Its wide-field instrument is a gigapixel-class infrared camera utilizing 18 H4RG detectors. It produces images as sharp as Hubble's, but a single pointing covers an area larger than the full moon. Roman will perform the high-latitude time-domain survey, staring at the same patches of sky repeatedly to find thousands of Type 1a supernovae to measure the expansion history of the universe. It will also perform the galactic bulge time-domain survey, staring at the center of the Milky Way to hunt for exoplanets via gravitational microlensing. It is expected to find thousands of planets, including rogue planets drifting alone in the dark and Earth-mass planets in Earth-like orbits, demographics that previous missions like Kepler and TESS missed. What happens when you combine these massive datasets? We unlock new realms of science. In cosmology, wide-field infrared surveys are the primary tool for understanding dark energy. By measuring the positions and distances of hundreds of millions of galaxies, astronomers can measure baryon acoustic oscillations, which are sound waves from the early universe that froze into the distribution of galaxies. This provides a standard ruler to measure cosmic expansion. They can also measure weak gravitational lensing. The gravity of dark matter bends light from distant galaxies, slightly distorting their shapes. By measuring this distortion over the whole sky, which is Euclid and Roman's specialty, we can map the invisible dark matter skeleton of the universe. These surveys also illuminate the era of reionization. The universe was once filled with opaque hydrogen fog. The first stars and quasars cleared this fog. Because this happened so long ago, the light is entirely in the infrared. Wide-field surveys will find the rare, bright quasars that powered this transition. In galactic archaeology, we can reconstruct the history of the Milky Way. Our galaxy is a cannibal that has grown by eating smaller dwarf galaxies. The debris of these meals is hidden by dust, but infrared surveys can peer through that dust to map the structure of our galaxy's bar, bulge, and halo. And in the realm of the cool, these surveys are the only way to find white dwarfs, the coldest brown dwarfs that may be as cool as the human body, testing our understanding of atmospheric physics. This shift to wide-field astronomy is also a shift to big data science. The Roman Space Telescope will send back roughly 20 petabytes of data. This is far more than any previous NASA astrophysics mission. No human can look at all the images. We rely on automated pipelines and increasingly on machine learning to classify galaxies, detect asteroid streaks, and identify anomalies. The next great discovery might not be made by an astronomer at a telescope, but by an algorithm running on a server farm. In conclusion, wide-field infrared astronomy has graduated from a niche subfield to the dominant mode of exploring the universe. We have moved from the grainy, low-resolution maps of IRAS to the crystal-clear billion-galaxy atlases of Euclid and Roman. By opening our eyes wide to the infrared sky, we are no longer just looking at the universe, we are immersing ourselves in it. We are seeing the dust that forms us, the energy that drives us apart, and the hidden worlds that share our galaxy. As SPHEREx and Roman prepare to launch, we stand on the precipice of a golden age where the entire sky will be mapped in color, depth, and time, revealing secrets that have been waiting in the dark for 13.8 billion years. Thanks for listening to G Fun Facts Online.